Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. We are discussing Chapter 8, Modeling Phase Equilibrium for Pure Components, and we are wrapping up our discussion of phase equilibrium calculations. So far, we've been modeling the vapor pressure. We started with the Clapeyron equation, which is theoretical and if applied to the liquid and vapor phases, says that the change in the vapor pressure with temperature is equal to the delta H of vaporization divided by the temperature divided by the volume change during this phase transition. The Clausius-Clapeyron equation is an approximation that is good for modest temperature changes. It's better when you're talking about kind of the lower range of the temperatures. As you approach the critical, it's going to not be very good. But we're making two different assumptions. One is that the vapor phase is fairly close to being an ideal gas, and that the vapor change in enthalpy or volume is fairly consistent throughout the change of temperature you're talking about. So that means that you're able to integrate it. It means you're able to eliminate the liquid phase V, and the volume for the ideal gas is going to be determined using the ideal gas law. And so what we end up with is that the natural log of the ratio of vapor pressures is negative delta H of vaporization over R times the difference between the reciprocals of temperature. And again, this one's really pretty good if your states 1 and 2 are not that different from each other in terms of temperatures. But you do have to have heat of vaporization. But we can go one step further. As long as we're assuming heat of vaporization is constant, then we can take the definition of the Pitzer acentric factor and eliminate algebraically that heat of vaporization. And in that case, we end up with log of the relative pressure at vaporization is equal to 7/3 omega plus 1 times 1 minus 1 over TR. This is like really exactly right at TR equals 0.7. But generally, once you get to a relative pressure of 0.5 or greater, this one's really going to be actually better than the Clausius-Clapeyron. But we have actually a really great approximation to the Clausius-Clapeyron that is empirical. Empirical means that it's based on fitting data. And the idea here is that if you look at graphs of the Clausius-Clapeyron equation, the graph of log of P versus 1 over T is really, really close to being just a straight line. And so therefore you could say that the log of P is A minus B over T, right? Just putting in a slope and an intercept for that straight line fit. And you can actually improve it a little bit by, instead of saying B over T, say B over T plus a constant. Now, sometimes this constant looks pretty large, in which case you're thinking that that makes no sense. But the Antoine equation is frequently fit with relative temperatures. So you do this for degrees C, for instance. And so therefore, the values are going to vary and they're going to be dependent on the units. Now, these are all done by fitting actual data. And so therefore, you want to be very careful that you are only using this for the temperature range that the data is good for, okay? Antoine equation works actually pretty darn well, but you can do even better. There's Wagner equation is one that you'll frequently bump into in the literature. It has a couple of extra constants that it's fitting, and it does a really great job. But again, the idea here is it's empirical, it's fit to real data. Another technique we can use is the Lee-Kessler So this is going back to the idea of corresponding states applied to vapor pressure. It's okay as long as the liquid is nonpolar. It's going to work, so for instance, with your basic hydrocarbons, but it's not going to work when you get to alcohols or water or those other polar liquids. But this one, again, it's done in natural log of the vapor pressure, and you get a naught term when omega is equal to 0, and you get a first term where which is basically when omega is equal to 1, and you add those two together. There are formulas, and those are shown here. So for the log of PR naught, it's 5.92714 minus 6.09648 over TR minus 1.28862 times the log of TR plus 0.169347 times TR to the 6th power. And the PR1 term, similarly, is going to be 15.2518 minus 15.6875 over TR minus 13.4721 times the log of TR plus 0.43577 times TR to the 6th power. And so you can use those, and they work fairly well also, and you simply need to have the critical properties to use those. So if you look at an example, cyclohexane has a vapor pressure of 13.01 kilopascals at 25 degrees C, and at that point the heat of vaporization is 32.8 kilojoules per mole. The critical properties, Tc is 553.5 Kelvin, Pc is 40.73 bar, and the Pitzer eccentric factor is 0.211. The Antoine coefficients are given in Appendix E of your textbook. And so, using no additional information, estimate the vapor pressure at 0, 50, 75, 100, and 150 degrees C using the shortcut Clausius-Clapeyron and Antoine equations. And then let's try and figure out, when we might want to use these various things. The first step in solving this is to find the constants for the Antoine equation. So in this case, if you look in Appendix E, A is 6.84130, B is 1201.53, and C is 222.65. These are valid in the range of 20 to 81 degrees C. To use these, we'll do the sample calculations for each of these at 0 degrees C. And of course, you could go through and do these for the other temperatures on your own. This is log base 10 of the vapor pressure is 6.84130 minus 1201.53 divided by the temperature is 0 plus 222.65. And so the log base 10 of the vapor pressure is 1.445. That means that you take the antilog of both sides, or 10 to the 1.445 power is the vapor pressure. That gives us 27.8 millimeters of mercury at 0 degrees C. If you do the shortcut technique at 0 degrees C, first step is to calculate the reduced temperature. So 273.15 is our given temperature, critical temperature is 553.5. So the reduced temperature is 0.493. Log base 10 of the vapor pressure is 7/3 times omega plus 1. Omega is our eccentric factor of 0.211. And then all of that is multiplied by 1 minus 1 over TR. TR in this case is 0.493. Calculating the vapor pressure, don't forget to take 10 to the power of whatever your answer you get here, is going to be 0.001258. This is the reduced pressure, so I need to still multiply by the critical pressure, which is 4,073 kilopascals, giving us a final answer of 5.13 kilopascals. The Clausius-Clapeyron equation, we need to have a fixed data point. We have 25 degrees C, and the heat of vaporization at that point is 32.8 kilojoules per mole. But since R is 8.314 joules per mole Kelvin, we'll use delta H of vaporization as 32,800 joules per mole. Substituting in the temperatures, don't forget that these have to be in degrees Kelvin. I end up with P2 vapor, or SAT, is 3.88 kilopascals. So this is a summary table of all of our answers. Now these have now been converted to kilopascals. Remember, Antoine gives us millimeters of mercury. But when we do the conversion at 0 degrees, Antoine is 3.71, shortcut is 5.13, and Clausius-Clapeyron is 3.88. At 50, Antoine is 36.2, shortcut 39.4, Clausius-Clapeyron of 36.2. At 75, Antoine is 85, shortcut is 87.8, and Clausius-Clapeyron is 87. At 100, Antoine is 174.6, shortcut is 175.5, Clausius is 185.9, and at 150, Antoine is 551.8, shortcut is 548.9, and the Clausius-Clapeyron is 648.4. So I think that maybe you might have noticed that at 50 degrees C, the Clausius-Clapeyron and Antoine equations were exactly the same, right? And at 75, all of them were fairly similar. At lower temperatures, Clausius-Clapeyron agrees more with Antoine, and at higher temperatures, shortcut agrees more with Antoine. So those are things that you should immediately recognize. But which estimate is the best, right? That's really the question. And the point is that it depends. The reason we have so many equations is because they all have times when they are the best. In this particular case, Antoine is only validated for 20 to 81 degrees C. So 50 and 75 are in this range. That means that really those are the only two where the Antoine is considered to be definitely the preferred method. Now, typically, Antoine is going to be not too bad as you move away from that, but really 50 and 75 are the only places where it is considered valid for use. Now, think through what our assumptions were on the Clausius-Clapeyron. We assumed constant heat of vaporization, and we had a fixed point at 25 degrees C. So things that were close to 25 degrees C, probably this is going to be fairly close to true. So this Clausius-Clapeyron technique should be pretty good for temperatures near 25 degrees C. Now notice that at 50 degrees C, where the Antoine we know is valid, the Clausius-Clapeyron gave the same answer, right? So that's kind of confirmation that this assumption really isn't that bad. 0 degrees C is also not too far off. As we get up to higher temperatures, though, further away from 25 degrees C, it's not going to be quite as good for the Clausius-Clapeyron. So in fact, at 0 and 50, where we're just plus or minus 25, Clausius-Clapeyron is really good, okay? It's not far off from what Antoine calculated at 0 even, and 0 is outside of the range of Antoine, but it won't be too terrible, okay? At 50, it's the same as Antoine. As we move up to 75 degrees, it's not quite as close. Okay, so I would prefer the Antoine at 75. But what about those higher temperatures? The shortcut equation, its rule of thumb is that you don't want to use it unless TR is greater than 0.5. And it's really best as you get to that 0.7 range. Okay? And in fact, that would be for the higher temperatures, that would be my recommended choice to use. And again, you see that they are not that far off of the Antoine, but I still think that Shortcut is probably better than Antoine because the Antoine has only been validated for data between 20 and 81. So this gives you an idea of how you can use the wide variety of equations that we have to calculate vapor pressure. In our last video in this series, we're going to look at a little bit of the theory that's going to lead us into our Thermodynamics 2 course and why being able to calculate vapor pressure is so important. Thank you very much for your time.